All right, good morning and welcome to our 7th lecture on the lecture series, Introduction to Structural Dynamics. And today we are starting on the forced vibration for multiple degrees of freedom system. You may recall that we started discussing about multiple degree of freedom in the last lectures, and it's always good to refresh or to do a recap before you come to class so that we can be able to move together. Today we're going to have a short class, a very short one, maybe an hour or less, and then we are going to see what happens. Of course, we're going to look at an example, solved example, and also some question and answer session. Maybe you have never subscribed to this channel. This is the high time to do so. We are growing, almost reaching the 1,000 subscribers. And I'm happy because the effort that we put in preparing this and archiving this here, I see it's helping many people. So subscribe, share, and like in this video, and also tell a friend to subscribe. Okay, thank you very much. I can see we are well logged in at 32. We are not going to wait much longer. Just a short recap of what we looked at last time. We talked about something I introduced called natural frequencies and mode shapes. And I wanted you to just have a feel of what are these that we are talking about. And I found a very good video explaining in brief just how you could tell about these. What are these mode shapes? What are these natural frequency and mode shapes? I just like you to just have a feel of what is it that we are talking about in this. So this is a short recap before we start on forced vibration. Let's look at what are these mode shapes. Okay. All right. I was just checking something there to ensure that we are on the same page. So look at this. Look at this carefully. I hope you can see that screen. Look at this carefully there. Then see sort of explanation.
Every structure has natural tendencies in the way it tends to vibrate.
All right.
And it's an inherent property of the structure, just like concrete strength or density. If we look in the lower left-hand corner, you'll see a formula for natural frequency. This is for a simple single degree of freedom system, but I wanted to point out the relationship between natural frequency and stiffness and mass. So you'll see that natural frequency is generally proportional to the stiffness and inversely proportional to the mass. We can also calculate natural frequencies for more complex systems. Even a simply supported beam has many natural frequencies and mode shapes. The natural frequency is just the frequency at which it oscillates, and the mode shapes are the
So you're looking at that. I've just paused briefly, just to mention something. These are just simply supported beams. Yeah, supported on this edge and on this edge. Okay. So of course, you know the load application is downward, up and down. So you can assume that in this beam, we have like a machine that is have got a rotor that is out of balance. That is causing an up and down harmonic motion. On this other edge, we have a building, a tall building, and as you can see, many stories. Yeah. So it's also showing the kind of vibration that are occurring. And here we just want you to have a physical feel or understanding of what are these mode shapes, what are these natural frequency of a building, and so on and so forth. And so that the terms that you introduced or what you have been mentioning about, you can see in a real structure what is it that we are talking about. So for the beam, you are going to see the different shape, the deformation that can occur as a result of vibration. Same case for the building. And what Engineer Hash is just doing is describing in a very simple manner, in a very easy way for you to understand what are these, what are these mode shapes, and what are these natural vibrations. And just a little bit, let me just go back slightly so that you can, from the start of this small clip about 2 minutes, that you can see what it is that we are talking about. So listen again once more, just once more before we continue. Okay. I don't know. It seems like there's Stop playing. Oh, sorry for that. Is there an issue with my internet or it's telling me that I should not have stopped the clip. Okay, I'm working on it. Just hold on. Oh. Okay. Let me just first stop share. See what happens.
Our deformation shapes that every structure has natural tendencies in the way it tends to vibrate. And it's an inherent property of the structure, just like concrete strength or density. If we look in the lower left-hand corner, you'll see a formula for natural frequency. This is for a simple single degree of freedom system, but I wanted to point out the relationship between natural frequency and stiffness and mass. So you'll see that natural frequency is generally proportional to the stiffness and inversely proportional to the mass. We can also calculate natural frequencies for more complex systems. Even a simply supported beam has many natural frequencies and mode shapes. The natural frequency is just the frequency at which it oscillates, and the mode shapes are the deformation shapes that correspond to each particular mode of vibration. So you'll see here for a simply supported beam, we're showing 3 different mode shapes. Mode shapes are actually unitless and they're often normalized. So 2 ways in which mode shapes are typically normalized are unity-based, where the maximum value in the mode shape is set to be equal to 1, and mass normalization, where the mode shapes are normalized in such a way that the mass matrix entries are all equal to 1. When we're looking at floor vibrations, we're typically interested in vertical degrees of freedom. So we're looking at these up and down motions like we're looking at in these simply supported beams. If we were looking at seismic, we might be interested in horizontal degrees of freedom and horizontal mass and entire building movements like the one we see up in the upper right-hand corner there. So every structure has many natural frequencies, and the fundamental frequency is simply the smallest natural frequency and associated mode shape. For those of you who took structural dynamics, you'll remember that we can solve for these natural frequencies and mode shapes in complex structures by solving the eigenproblem. So we solve for the eigenvectors, which represent the mode shapes, and the eigenvalues, which give us the natural frequencies.
All right, good. That's what I wanted you to have a feel about concerning last week. And you can watch the whole clip and other explanations on this from his channel. I think I'm going to share the link to this video. You can watch it later on. It's a very interesting one. So that now, when we are talking of, when we are solving this problem, if you recall, when we are solving this problem, or in brief, what he was saying is that every structure has got a tendency to vibrate. And there is the natural frequency at which they vibrate, of course, now that you're talking about the solving the natural frequency, they will deform, the structure will deform. For each vibration, it will have a different shape of deformation, what you call the mode shape. And we talked of mode shape being unitless. Yeah, being unitless. And we do this by normalizing. And a number of ways of normalizing or setting the maximum value to 1. And that's why you could find like in this case here, you found or we were using or setting the deformation, the value for the second part to be 1, so that you are expressing this as a ratio, okay, to normalize the mode shape. And this was again expressed or explained in this part. So this paragraph number 78, this slide is highly summarized, and that's also that was being explained in that small video about how we get the mode shape, how to obtain the mode shape. The mode shape when you solve the eigenvalue problem. Yeah, we are solving these eigenvalue problems. So we solve by getting the eigenvectors, which are the mode shapes, and then the eigenvalue that you obtain. These are the natural frequencies. And of course, the last part which was explaining about the phi n. This was to ensure that we express the mode shape as unitless form. I found it important to explain further on this so that it's not just a matter of going through the course, but also understanding what is the physical implication of this in a real structure. Okay, so let's move now to our class today. To our class, we are on force vibration. And to make now matters again a little bit interesting, we know, of course, we are talking multiple degrees of freedom. We start with the lowest degrees, which is a 2. Of course, for it to be multiple, it has to be more than 1. So the smallest that you can ever have is 2 degree of freedom dynamic system. And then we make matters interesting here. We said that at the first floor level, there is no forcing function. There is no externally applied load. So the raw structure, the equation will be free vibration. But for the second, we are applying the external load only at the second floor level. Okay. As usual, of course, mass is concentrated at floor levels. Columns just provide the stiffness. And the beams or the girder level is very rigid, so no rotation at the floor level. And that's why it makes it a shear building. That's the definition of a shear being. There are no rotations at the floor level. So you're talking of first undamped vibration. So undamped meaning even at this stage we do not have the coefficient C. Yeah? So you see the equation of motion. What happens is that we reintroduce. So the first one, of course, the first one is just as the way we did with the free vibration. So we're looking at the equation 94. But for the second floor level, remember the equation of motion for this structure is the overall equation, all the equations combined for the different levels. I mean, not levels. You can talk of levels or stories for the different stories. So the second floor level, now the external force F is, we have a value, F naught sine omni. So we are assuming harmonic loading. And of course, if you go back now to a single degree of freedom, because we are borrowing from the same, we are continuing from the same. I believe this was either lecture 3, which we are talked about forced vibration for single degree. We found that typical solution for this kind of an equation 94, especially part B, is of this nature: ui sine omni and u2 sine omega t, or omni capital omega. So these are the typical solutions for the steady state response. And this is what we are solving to get the value U. So what you just need to do is now you substitute the equation, which is the solution, equation 95, into the problem. And you, of course, you cancel the common factors that they require. You're going to get equation 95 as a steady state response. And I have summarized, highly summarized, because, of course, we did step-by-step solving in the previous sessions. So in this case, I feel like it's not that necessary to continue repeating the same. But for your case, you should be able to just substitute and come up with this equation. It's very easy, as ABC. So for our understanding, I found it necessary that we move with an example. An example as shown here, example 9. And you're given a 2-story building. The mass is given for 2 levels. And the second floor level, of course, there is an external load that is applied, forcing function. You know, of course, 2 degrees of freedom, and there will be 2 displacement, U1 and U2. You're given the flexural rigidity for the column, EI. What else? The height, floor-to-floor height, and the bay length. Of course, now the length of the length of the beam. So you was required to determine the steady state response of the 2-story building shown. So what do? First, we need to get the natural frequency. Of course, we are using equation 94, 95, and 90. They should be 96. Okay. Now, the natural frequency, this, if you are careful enough, you will note that this is the equation that we continued from example 8, from the previous lesson. And if I can just go back to that, the example that we solved, this is the example we solved in example 8, okay? And the example 8, there was no forcing function. And remember, just explanation from Engineer Hash, he talked about that every structure have got a tendency to vibrate, yeah, to oscillate. Even the structures that you are living in, it might be very small relative to a structure, but it have got tendency to vibrate or to oscillate. So this tendency is not as a result of any externally applied force. And that's what we talk of free vibration. Okay, and as you can see, whether we apply the external force or not, the natural frequency are independent of that. The natural frequency, the forcing function will just come to exaggerate or to increase, to add to that as proposition effect. And that's why you find that in this building, we obtained what we call, we obtained our natural frequencies, the omega n, and of course the mode shape. So we are talking about this omega. The natural, of course, this angular frequency. You can talk of the linear frequency, Fn. We obtained that, we calculated this. So the same case, even when there is this loading, external applied force, we think the natural frequency for the frame was determined is the same, okay? But now we have an additional forcing frequency. Forcing from this force F2 at the second floor level. Remember the equation for this, or the, we talk of looking at some annotation, we talk of the forcing function being Ft is equals to F naught sine capital omega t. So in this case, capital omega is 20. This is the external, I mean, this is the forcing frequency. And F naught is equals to 10,000. Good. So the forcing frequency is given. And you're saying, since the frequencies, it doesn't rhyme with either of these. So remember, we are saying, if the natural frequency of our structure correspond to any external, for the forcing, the frequency of the forcing function, then resonance will occur. And you know, when resonance occurs, of course, the amplitude becomes very great and very high, which might result, and this is what results in maybe the collapse of a building when there is the resonance. That interference, constructive interference of the waves, they end up magnifying the amplitude beyond what can be taken by the material that we have used. Remember, the amplitude is the maximum displacement at any one time. Therefore, the steady state response, of course, now to obtain the steady state response, we are taking this equation 96. We have found this, you can do the correction. But if you correct at this stage, now you have to correct everywhere. This is equation 96, because we found in the previous slide, it was equation 95. So with that, we are saying you just need to substitute the values for omega 1, omega 2, and all that. You're going to get those equations. Then solving, you're able to get what is U1 and U2, because these are the maximum displacement or the response, maximum response. These are this is the amplitude, You see, the amplitude here, the capital U1, amplitude of our steady state response. Remember, our response varies with the time. That is the value U1 at the first floor level. U1 will vary or will change with the time. U1 changes with time because of it's a motion, it's a dynamic motion. But it goes our forcing, our motion will have an amplitude. And this is the amplitude U1 that we are talking about. So now, if you solve for U1, you're going to get the coefficient, of course, for each one of the steady state response for the first and second floor level. And therefore, the steady state response is this equation here. So the issue was to determine what is U1 and U2 using that equation. Very easy. But let's spice things up. Let's have damping. Damping is when now we reintroduce the dashboard or this the damping component, and we introduce the damping at either of the floor levels, not either, but both of the floor levels. So C1 and C2, and of course we can rewrite this in using mass spring model as shown here on the photo around screen. And from this, you can be able now to isolate the free body diagrams to see all the forces that are acting in it. Of course, this is what we did in the previous lecture 6. And what have just been introduced is the component C. Yeah? You can see the damping part. C1, U1, C2, U2. And this is a SIGO. This you should be very careful because, of course, we are using annotations to simplify our workings, to avoid writing the overdicts. This is not acceleration. I'm saying these are like there are two dots. This should be one dot here because that's acceleration. I know this is a velocity, it's not acceleration. Okay. So, of course, now our equation of motion, this component comes into play. So remember this equation of motion, you have derived it from this. Okay. Or expanding the one that we derived from free vibration. Okay. Same case for the second component, you have the C2 coming into play. Now, if you assume that the applied forces F1 and F2 are of that form, now we have, of course, we want to deal with harmonic loading, making our working easier because of these are easy to obtain the derivatives. Okay. Remember, the forcing function can even be a step loading. We can have a constant load, or we can have ramped loading. We can have even general loading. Remember the case we solved the Damer's integral. But if we now start solving the Damer integral, we found that the process, those tabulation are a bit tedious. So we might lose the focus of our working here because our focus here is to understand about the response for a multiple degree of freedom. So that's why we are using a simple harmonic loading. So the same case, we have assumed that the harmonic loading for either at this flow level is of this nature. And we are saying this can be expressed in complex form. Remember the Euler acceleration. We have been using them throughout our course here, so that because it helps us to simplify as well as to deal with the complex numbers. So in the same manner, we are saying the equation 97 can be rewritten in using the Euler acceleration in complex form. Now you have introduced I, which is a complex number. But we note that only the real part of that equation 98 is the applied force. So you substitute that 98 in 26 to obtain this equation. Of course, I'm not going to work it out because I have already worked it out here. But it's always good as a student, you sit down, you do calculation or evaluations so that these things stick into your mind and memory, and also get into your fingertips. And of course, we know the solution of this is of the form here. Remember, this now we have borrowed also from the first vibration for a single degree of freedom case. Now we are extending it to multiple. That's why you are saying we already know what are the typical solutions that we can obtain. And in the single degree of freedom, we knew where they are coming from because we are borrowing from. We knew that we are dealing with ODE, either homogeneous or non-homogeneous. So it was very easy to know what is the typical solution for the same. So equation 101, 100, 101, and 102, this is just simplifying equation 99, working it out. You are given the steps of what is done in each of them, substituting and finding its derivative. Equation 101, and retaining on the real part, you get the response in equation 102. Yeah. So don't be overwhelmed by these calculation or derivations. It's just as long as you know how to get them to differentiate, then it's nothing much. It's just what we did in the single degree of freedom case. This for your understanding, maybe for exam purposes, you might not be required to know something like this. But again, I say that our learning is not just for the exam purposes. We need to understand where this thing comes from, so that we do not do what we call rote learning, but at least we build our understanding of the different concepts that are employed in some of these engineering structural mechanics procedures. And especially when you talk of structural mechanics, I find many people, when in the final project, they always like to go into materials. But remember, even when you do materials, it's always very important to know what are the underlying equations and the relations that we employ. That's when you talk of the structural mechanics. What are the mechanisms that yields what we obtain? Okay. So you're saying that speaking of Damer's integral, they used a more complicated form of Simpson's rule to integrate. Is it necessary? Can I just use the normal form of Simpson's to solve for an end? Yeah, of course. Oh, I don't know why you're saying they used a more complicated form. If Simpson's rule more complicated, And can we complicate Simpson's rules? Maybe what you should be saying is that they tabulated, they had so many columns. You can simplify it. It's a Simpson's rule. As long as you are following the procedure, as long as Simpson is Simpson. Okay? Yeah. What I found is that from that table, the one that we did in exam, you don't have to have all those columns, many columns, or too many. But I believe they were splitting them so that you can understand at each stage what is happening. You can have yours as compact as possible, but at the same time, not losing the flow. Because you find like people want to simplify things, but there is some working behind which you are not showing. Okay. If you find like there's some you're working behind the booklet that you're going to get the summary and then bring it there, then what you're doing is just hiding information from the reader who will come later on. All right. Good. And Humphreys, you have been so active in this class. I believe if there was a medal, we would have awarded it to you. Other people are just quiet. Okay, that's commendable. Again, just a small example, similar to what we had, but in this case, we have the dumping. And again, because we have so many of these examples, this being example 10, and also many tutorials are there. So it's kind of a practice that you can do. You are given the guide that what to do. You're given the example, but you are told it's the same building, the same example as in the example 8. So of course, the natural frequency rollers are the same. Then you assume that in this example, the damping coefficients are introduced, C1 and C2 respectively. Okay. And they are proportional to the spring constant K1 and K2 with a factor of proportionality H1. So of course, we are saying C1 is equals to H1 K1. So you can be able to obtain that. So you are required to determine the steady state response. Of course, what is U1 and U2? The equation U1 and U2. How does it vary with the time? So what you just need to do is substitute the given numeric values of equation 101 and so forth, the capital, the amplitude, U1 and U2. And then you substitute the equation U1 and U2 into 102 while ignoring the imaginary part to obtain the response. So you're just using this equation the same way that you have solved the previous example where there was no damping. You just need to get what is, remember, this is the response, the small letter U1, the response, the capital letter U, C1, of course, this is the amplitude. This is what we first determined. So the same manner that we solved this equation in a simple manner that what we do, the response is this, equation 95. Okay, so you have the problem equation 94. We have the solution to the response equation 95. We have equation 96. This comes only the common factors. You can be able now to use this equation to obtain what is the coefficient, because from 95 you need to know what is U1 and what is U2, the amplitude, and then so that you can know what is the equation for a steady state response. Same case when there is damping. When there is this damping, okay, when there's this damping, what you just need to do is you're utilizing, we have the problem equation 96. Then equation 98 helped us, 97 and 98 help us to simplify our equation using the Euler's relation. So you have equation 99, 100, and 101. So either of these you can use to obtain. It's simplifying to be able to obtain what is the U1 and U2. So you're solving for what is UC1, UC2, so that you can be able to substitute in the equation 102. So the work is here, substituting the values in equation 101 to be able to obtain what is the coefficient UC1 and UC2. And then you can be able to substitute in equation 102. So that's work for practice. I'm seeing Dennis, you're saying, could we get an example that has less columns? Easily tabulated. What do you mean, my friend, Bana? Don't be that lazy. Eh? The tabulation was for your understanding. If we just summarize the equation, I believe you are talking of this. I believe you are talking of this. This example. Right? I mean, it's very simple here. It's just a matter of punching in the calculators. Okay. So, like what you are saying, do what Humphreys was saying. We are using Simpson's law, Simpson's rules, and then the one that used to simplify equation 83, 84, and so on. Because our overall goal is to obtain equation 85, which is the response of our structure. Okay, so no matter how many columns you put here, no matter how much you squeeze it or you expand it, that is your own liking. And the good thing is that this one you can do it as a practice because you have an assignment on the same. Okay, so for me, I don't think you can get example that have less columns. If you look into the books, different books in the internet, you can obtain that. It will be workable from your side if you feel like that. Okay. Okay, where were we? We are in this. We are solving our problem here. Oh yeah, I think we already finished the procedure. So what I'm saying here is that you just need to go through this, just the same procedure that you have done, use the equation that you have derived to be able to obtain what is capital U1 and U2, the amplitude, and then you get what is the response. Okay. And it's as simple as that for multiple degrees of freedom cases. And I want to stop there. I say today class will be a very short one because as you can see, there is nothing much to talk about here. I believe you have this one example in the assignment that you're giving me next week. So as you do that, of course, it will help you to address or to look into this. Yeah. All right. Any question, any other question? I'm looking at the chat section. I cannot see another question that is not answered. So any other query that you might be having, you can always leave in the comment section later on. Later, maybe I believe if I can trace that link where I got a small video if you want to watch much. But the other things that he was explaining apart from that basic definition were other things that we have covered about structural dynamics. Okay. So if there are no other questions, let me stop here. And thank you for attending the class. I hope you continue preparing yourselves. This should be the 9th week, so you're almost coming towards the end. So next week, let me get those assignments and the CATs. We see the way forward. I look at how the performance was last year's sitting cut was very dismal. So I wanted to see, to just have a high rate, but don't be so happy. We might try to add another sitting cut for those people who want. Okay. So bye-bye for now. That's the end of our lesson.